In this video and in the next couple videos, as a matter of fact, I'm going to be talking about multiple identical particles. And this video is actually going to get into the Pauli exclusion principle. And so when we are talking about multiple identical particles, so the wave function of a single particle, so this is the time-dependent wave function. And so for two particles, we just now have this R1 and R2. So the Hamiltonian for the time-dependent Schrodinger equation becomes this. And so we have this kinetic part for the first particle, and then this kinetic part for the second particle, and then we have to have a potential for both particles. And then we can do a separation of variables, so we're separating out this time part of it here, and then this time independent part here. And so if we look at just the time independent part, then we have this. So this is the kinetic part for the first particle and the kinetic part for the second particle. And so we can look at two sort of special cases here because this can be this is going to be a very difficult differential equation to try to solve. And so, you know, like with a lot of things in science, we're going to make some sort of approximations. And so there are two sort of approximations we can make using these two different sort of special cases. So the first one being non-interacting particles, and the other one is what is known as central potentials, which is just when two particles are only interacting with each other and to the potentials that both of them have. So in the case of non-interacting particles, then the potential energy is just the sum of these potential energies, which gives us this. So now we have the kinetic part for the first particle, the kinetic part for the second particle, and the potential for the first particle and potential for the second particle there. And so the wave function, which is this, we can then do another separation of variables. So this is the wave function for the first particle and the wave function for the second particle. And so the reason we can do that is because we can just pair this kinetic part with this potential part, then this kinetic part with this potential part. And so what we end up doing when we do that is we end up getting these two things here, which is just having those things paired together. So the kinetic and potential part for the first particle, the kinetic and potential part for the second particle. And so we end up with these two different energy eigenvalues here. And then so we put them back into the time-dependent Schrodinger equation, which has this this complex exponential here. And then so we can just take the product of them because that's what we were doing up here. So it's just we did that separation of variables, so we can do the product of them. So it's just the product of the time-dependent wave function for the first particle and the second particle. So we end up putting those together. We have the time-independent part here, and then the time-dependent part there, and then we can just put that back together. So now we're sort of absorbing the time-dependent part back into it. But then Griffith talks about how we can do linear combinations of this now. And so he gives this example here where we have this term here plus this term here, where this term is essentially what we just got up here. And these ones that are in the same term together, so I have them sort of color-coded here, are entangled particles. And so if we take a measurement and find that the first particle is in this state here, so we find that it has this energy here, then we know without even measuring it that the second particle will have this energy right here. But on the other hand, and these have these coefficients out here telling us about the probability of getting each one of these. So there's this probability of taking a measurement and finding this this C state right here, which would be this EC energy, and then we would know, because it's entangled with this other particle, that that would have this energy E sub D here. And then so for central potentials, which, like I said, is when the two particles have their own potentials, and that's how they're interacting with each other. We just need to do a separation between the two particles. So we're looking at the separation between particle 1 and particle 2, because their potentials are interacting with each other, and those potentials are a function of the distance from each other. And so using a proton and electron, like in a hydrogen atom, it becomes a single body problem, because the proton is a lot heavier than the electron, and so it's not going to move. Its movement is going to be negligible compared to the electron. Sort of the same thing when we're looking at the gravity, like between the Earth and a person, where technically there is some movement of the Earth when a person is moving relative to it, but it's so negligible that we can just think about it in terms of the person moving. All right, and so if we have multiple particles, such as 2 electrons in a helium atom, which the helium atom, the protons have the 2q, so the proton 1 has a charge of q, the proton 2 has a charge of q, so we have 2q positive charges, and helium has 2 protons, and we use the Coulomb potential here. So the potential is this. So I have these sort of subscripted here. So this first one, which is positive, because remember, in the Coulomb potential, positive is repelling and negative is attracting. And so this one here is for the electron repulsion. This second one is for the first electron attracted to both protons, so treating both protons in the nucleus as sort of a 2+ charge, and then this last term here is the second electron attracted to the 2 protons to the nucleus. And so we end up getting this, and you can see how this can start getting more and more complicated as we start adding more and more particles. And then so we get to the Pauli exclusion principle, and so what that is saying essentially is this assumption that we were using above doesn't really work, because 2 electrons are sort of indistinguishable from each other. And there's sort of a scientific and even sort of a philosophical problem with this, about the fact that any 2 electron particles are sort of indistinguishable from each other. And so this doesn't really work, because we can't sort of like paint a sign on the first particle saying that this is particle 1, and then a sign on particle 2 saying this is particle 2. And so there is this sort of well, they sometimes call it like an exchange interaction with each other. And so what we need is one of these to formulate right here. And so the first one, the difference between them is this has a plus in it, and this has a minus in it. And so what you see here is that we have this particle here, the function for the A state here, which is acting for particle 1, which is for particle 1. That's what the R1 is for. Plus we have this, so the B state for particle 1. And so we're saying that there's a chance that particle 1, there's a superposition really of particle 1 being in the A state and particle 1 being in the B state. And then down here, this is what's called antisymmetric. And so we will take a look at sort of the difference between these two. So what it means in practice is in the first this first one up here is that there's no cost to exchanging the two particles. Whether you call a particle 1 or 2, it doesn't really matter because they're perfectly interchangeable. And this is because if we rearrange the subscripts, we essentially just get this. We just get this equals this. And in fact, that is sort of what the symmetric is defined as, is this, where when we rearrange, so this 1 and this 2 here to 2 and then 1, they're just equal to each other. And so those are equal to each other, and that's why it's called symmetric. And these particles are what are called bosons. And so if you're ever, if you have read, a bit about like popular science on this, you've probably heard of bosons. You maybe even heard of like the Higgs boson and stuff like that. But bosons are sort of force-carrying particles. So like the photon is a boson and things like that. And these have an integer spin. So a spin of 1 or 2 or 3 or so on and so forth. But for the other one, when we change the subscripts, this ends up equaling 0, and this tells us that this with the particle in the first position, the second particle in the second position is equal to the negative of the second particle in the first position and the first particle in the second position. So what this means is that the two particles can't occupy the same state. If they did, their wave functions would cancel and go to 0. That's what it means when we have this 0 here. So those particles can't occupy the same state. Those particles are called fermions, and they have half-integer spin. And so fermions are things like electrons and quarks and things like that. And so I guess you can kind of think about it in terms of like the matter particles. So when we talk about the state of a fermion, well, this would be the state of 2 fermions right here in, say, an electron. Then what we're talking about are actually the quantum numbers, which is the N, L, M, and S. So the principal quantum number, the angular momentum quantum number, sometimes called the azimuthal quantum number. M is the magnetic quantum number, and then S is spin. And if you remember from an earlier video that I've made, where I was looking at the solutions to the Schrodinger equation for the hydrogen atom, what we ended up getting was this big long thing here. And we see that this has the N, L, and M here. And so the first 3 quantum numbers in this solution to the Schrodinger equation for a hydrogen atom. But then we have spin, which can kind of seem a little tacked on, but you need relativistic quantum mechanics to fully account for it. We are talking here about non-relativistic quantum mechanics. So there's kind of the beginner's quantum mechanics is non-relativistic. Then you can sort of move to relativistic quantum mechanics, and then after that you sort of go to quantum field theory, which is also a relativistic theory. So it takes special relativity into consideration. So in practice, what this means is that 2 electrons, if they share all 4 quantum numbers, it would have to just be the same particle because they can't both occupy the same position. So if any 2 electrons have the quantum number n equals 1, L equals 0, M equals 0, which is the 1s orbital, then we have to have an s. One of them has to have an s equal half, and the other one an s equal minus half. So a spin up and a spin down, or they could not share the other 3 quantum numbers. And so we will actually see in this video and then the next video, when we talk about this symmetry and anti-symmetry, we're talking about the spatial and the spin quantum states. So the spatial is this one up here. So that's what this whole thing is up here. That's the spatial, and then there's the spin. And if the spatial is symmetric, then the spin has to be antisymmetric, and if the spatial is antisymmetric, then the spin has to be symmetric. So I'll get into that a little bit more in the next video, but for now we can just think of symmetric and antisymmetric sort of without spin, or I guess essentially sort of absorbing spin right into the wave function, if you will. So once again, this is called the Pauli exclusion principle. So if we have this where it's not equal to 0, this is because, for instance, the first and second state have different spins. So we're essentially saying that the spin is accounted for in these wave functions here. So we're sort of absorbing the spin into the wave functions. But if we switch them, then we get this, which is equal to 0. Because if we say that we could make the switch, then it's saying that the two electrons are indiscernible, meaning that they have all four of the same quantum numbers. So two electrons in the same shell, so the 1s2 shell, which is the sort of ground state shell. This is the first shell that gets filled. Both are able to occupy the same space only because they have different spins. So that's kind of getting at what I was talking about before, where if they are symmetric in space, being able to occupy the same space, then they have to be anti-symmetric in their spins. So if we don't take spin into account, then two fermions tend to be farther apart. So the expectation value for the square of the distance between two distinguishable particles A and B is this. So I'm skipping 2 pages of math from the Griffiths textbook, which is mostly what I'm following along with here. And I thought about putting the whole math in, but I ended up deciding that I thought it was perhaps more obfuscating than clarifying. But the cutting to the chase here, so the distance between these two particles is this. While for two identical particles, it's this, which we see has this extra factor on the end here. And so this factor, so the minus is for bosons, meaning they're closer together because we're subtracting some distance off of it, while plus is for fermions, which is adding some distance between them. And so that's sort of pushing them apart, which for me, so this, it's often thought of as a force for this, but and sometimes you even see it called like exchange forces, but it's not really a force. It's something that's quantum mechanical and doesn't really have like a classical counterpart for it. But it's still sort of moving particles closer together or further apart in the case of these fermions. And so for me, I like to think about it that they're excluding each other. And so if you have the two particles and they're they have the same spin, then it's going to push one into sort of a higher energy level. But if the particles are far enough away, then this x AB here actually vanishes, and so there would be none of the wave function overlapping. So this is what I mean by the wave functions overlapping, where we have some overlapping here, and if they are fermions, then they are sort of being sort of pushed together somewhat in space. If they have their opposite spins. All right, so if we take spin into account, we know, and this is from an earlier video, that the singlet is antisymmetric with respect to spin, meaning that it's symmetric with respect to position. So this is antisymmetric, that's why it has the negative with respect to the spins here, while the triplet is symmetric with respect to the spin, so antisymmetric in position. So what that kind of is talking about. So when something is symmetric in position, they can sort of couple up like this. So this says no unpaired electrons. So these are paired electrons. So that pairing is the fact that they are occupying the same space, but they're just antisymmetric with respect to spin. So if one is up and the other is down, then these two things can occupy the same space. Whereas here, where it's symmetric with respect to spin, so that's what we have here. We got the plus right there, and then this is obviously symmetric with itself, and this is symmetric with itself. So then we have to be anti-symmetric in position. So this shows these as well, it says unpaired, but it kind of shows them as paired. And I'll actually show in the next video that one of these electrons would have to be like pushed to a different position, which would usually be in like a higher energy state. So where we see that the singlet has the paired electrons, hence why they can both be up or down. This means that the singlet, which is anti-symmetric spin because they are distinguishable, has to have symmetric spatial function, which is why they are paired and occupy the same orbital. And then, so we can actually think about this with Slater determinants, which Griffiths doesn't actually get into this. And I got this from my physical chemistry textbook. So it's just Physical Chemistry by David W. Ball, and I'm using the second edition here. And so a determinant is just this. So it's looking at elements of a matrix, but you just take the upper left times the bottom right and multiply them, and then subtract the product of the well, it would actually be the upper right and then the lower left. So I mean, these things commute, so it doesn't really matter, but just because this is the way that I'm actually using it down here, I will make that switch, but it doesn't matter up here at all. But once we get down here, then well, I've changed it, so I'll just be using it that way. So where does 0 if two rows or two columns are exchanged, just like with the anti-symmetric fermion? So like if we switched some of the rows or columns in here, then you would actually get something that gives you 0 if this is already like a non-zero determinant here. So we have here, so this is essentially the same thing, so we end up with this, which is the same one from above up here. So it's just that same one above up there. So that is not equal to 0. But even with it color coded, this looks like just kind of a big wall of sort of symbols. But you see that these red B's are now down here in the column rather than in the row, or the column up here are now down in the row down here. And so we flip them, and so this will end up being equal to 0. And so that's why these Slater determinants work. So we can do the same thing for three different particles here. And what we will see is that if two of the electrons have the same spin, so up in here, then we could get one of two determinants, which are one of these two. And by the way, as usual with these videos, these lecture notes will be linked to in the description down below if you wanted to sort of look at this more slowly by yourself. So a lot of this stuff, isn't actually showed in the textbooks, but I like to just kind of put it up here to be very explicit about what's actually going on. So even in my general chemistry textbook, it shows these two determinants here, but it doesn't actually like lay them out here if you actually take the determinant. And there is a little tutorial about how to take determinants of 3 by 3 matrices that will be on the last page of these notes if you wanted to look at that in a little bit more detail. But the sort of the take-home message here is that either one of these determinants would be 0 if there is if two of the particles are spin up and one down, or if one is spin up and two down, which would tell us that one of the electrons would have to move to a different orbital. And so that's actually what happens like when you finally get to lithium on the periodic table. So hydrogen has a single electron which can occupy that first orbital. Then helium has another electron, and both of those are spatially symmetric, so they occupy the same space, that same orbital, but their spin is antisymmetric, and so one has a spin up and one has a spin down. And so if you try to put another electron in that same orbital, so occupying that same space, it either has to have a spin up or a spin down, and that can't be, because then two of them would end up, of the three, would end up having the same quantum numbers, which would cancel out, and you would, end up getting equal to 0. And so one of them would have to get sort of pushed up, by that pseudo force, I guess you could call it, into the next orbital up, which would be the 2s orbital. All right. So anyway, so we can think of. So once again, it's called the exchange interaction. Sometimes, like I said, it's called the exchange force, even though it's not really a force. It's a purely quantum mechanical effect. But then here I have a generalization of the exchange, and so we can define an exchange operator. So this p hat here. So we're acting that on sort of an arbitrarily many particles in this wave function here. And it has to be plus sort of the reverse of all those particles here. So now we're going from n down to 1 rather than 1 up to n. And so it's plus if it is symmetric and minus if it is antisymmetric. So the eigenvalues are either plus 1 or minus 1, because there's sort of an implied 1 up here. And obviously, if you act on this system, then again, you would just get the same system back. And so p hat squared, which is just doing the operator twice, is just equal to 1. So the system goes back to the original. And if the particles are identical, so if we, in the Schrodinger equation, just had our m1 and m2 be equal to each other, and we had our two potentials, so with the R1, R2, and then with the R2, R1 equal to each other, the Hamiltonian will actually commute with this operator right here. And so that means they are compatible observables, which in other words means that you can know the energy and the spin of a particle at the same time, allowing you to know this state right here. And so the product rule, so if we want to look at sort of the time dependence of this this exchange operator, so this p hat here, so we are just taking the time derivative with respect, or we're taking a derivative of this with respect to time. So we do the product rule, and there's quite a bit of math here. I think I'm going to sort of rush past a lot of that and sort of skip to, or cut to the chase here. So once again, we know that the Hamiltonian and this exchange operator commute, and so when we have the derivative of our exchange operator with respect to time, it ends up being equal to this commutator here, and so it is equal to 0, which in the end just means that if a system is symmetric, then it will stay symmetric, and if it is antisymmetric, then it will stay symmetric. The actual symmetric or antisymmetric state of the system is not actually going to change over time, just sort of on its own. And so that's, sort of what going through all this math is here. And so this is from Griffiths, and he kind of skips through a lot of this math, or he refers to something earlier in the book for this, and so I actually just went through and explicitly put that all in there. So once again, if you want to check that out in more detail on your own, then these notes will be linked to in the description down below. Yeah, and so this is determinants of a 3x3 matrix. But anyway, so that is everything about the well, not everything. It's the Pauli exclusion principle in a nutshell. And so the kind of the big take-home message, and probably if you've ever taken like, a chemistry class, the thing you know about the Pauli exclusion principle is that particles in an atom can't have all of the same quantum numbers. So, if it has like, where was that? So if it has the L, M, and S all the same, then it would have to be in a different N. So if N, L, and M are all the same, then it has to have different spins and so on and so forth. And so, it's with these quantum numbers that you actually build up the periodic table of elements, and it's why the periodic table has the shape that it does. But I'll be talking about that more in the future. Like I said, the take-home message for this one is that in an atom, no two electrons can share all of the same quantum numbers. And so if something is symmetric in space, which means that it shares this first three quantum numbers, so it's N, L, and M, it's principal, angular momentum, and magnetic quantum numbers, then it has to be antisymmetric with respect to spin. So one has to be spin up, one spin down. If it's symmetric with spin, then it has to be antisymmetric in space, which means that one of the numbers N, L, or M has to be different from each other. And so that is, like I said, kind of the take-home message from this whole video. And I will continue talking about these multi-particle systems in the next probably few videos after this. But anyway, I hope you found this video helpful, and I will see you in the next one.